And of course, you really need to take motor control. I think it's part of your core anyway. Uh, because when you get out in the field, PLC's not done away with relays. They're delegated now mostly to handling high-powered situations. So you very seldom see the PLC run a motor. You see a PLC energize a relay, and the relay runs the motor. So we still have most control sections now are built up of two major parts. We have what we call the control section, which is going to be low voltage. And then we have what we call the power section, and this is where your high voltage is going to be. That's the cabinet that will definitely get you killed if you get in there and don't know what you're doing. So the control section is probably, now it's very popular to be DC, 24 volts DC, can cause some problems, and it doesn't mean it can't shock you, but it's extremely unlikely, that it's going to be fatal. If voltages that low gave us problems, then we'd be knocking people off every day when they touch the terminals on their battery. A battery has 200 or 300 amps available to it. But what determines the amount of current that flows through your body? I is equal to V over R. So you get into 12 volts and you got a couple 100,000 ohms worth of resistance. When you touch the terminals on a battery, there is current flow through your body because there's a path. But it's just so what? It's just so little that you can't even feel it. And it doesn't cause problems. So, this should be this should be in the first module. So, in motor controls, you learn a logic called relay ladder logic, or RRL. And of course, this is where automated systems have been around for years. And of course, what gave us the ability to do a lot of automated control is using something we refer to as relay logic. So back in PLC 1, you learned about knots, right? You remember how to do a knot? Not a knot, but knot instruction. We had ands, ors, nands, nors, and knots. So y'all remember how to hook the contacts up to do that? Are we okay? And then, of course, we had timers available to us in motor controls. So when you take motor controls, you'll learn a lot about timers. We have different categories. And then we had counters. Counters are usually electronic devices. The only one I've ever seen that would you could actually preset it and then allow it to count for you. And then after that, we get into some of the instructions that we're going to be dealing with this semester. And of course, you learn symbols. We still got to know the symbols for relay logic, because when you draw the way you connect up the inputs on a PLC, you draw using the electrical symbols for push buttons and all those other devices. We're going to deal, of course, in here we're dealing with PLC ladder logic, or PLL. This is going to use a programmable controller, and of course, we're going to shift over to these guys right here. Usually we have two rungs, and all the circuits are drawn. So y'all know what a rung is, right? Y'all know why it's called a ladder diagram. Are y'all okay there? Any questions there? And so what is a rung? It's what? It's a circuit between L1 and L2. So a line is so if I come over here and So it's a circuit. So I could come over here and, let me draw here. So I could come over here and do this. And let's say, we'll just put a push button. And then I put a stop button. So how many lines does that rung have in? 2 lines. So we can't say it's a line between L1 and L2. It's a circuit between L1 and 2. So I could come over here and I could come over here and do this. And now all of a sudden that rung has what? It has three lines in it. So a line is just, it's one of these vertical things. So a rung is made up of one or more lines. So in relay logic, and this is also true in PLC logic, even though it kind of varies a little bit. So a rung is a circuit that runs between L1 and L2. It can be a parallel circuit. Of course, the input device does not determine what type of circuit it is. What determines what type of circuit it has is parallel circuit, right? And then the other circuit we have is a single load series circuit. And of course your loads, good practice is your load goes on the right, and we usually refer to this as L2. And then your control devices go between L1 and the load. So a relay logic will have one or more rungs. So these are relays, guys. So this is what's nice about a relay, is that first of all, we can use relays to electronically or electrically control a circuit. And we can also use it to get gain out of it. So the coil might be rated at 24 volts DC, and then over here we're switching 120 volts AC. So that's a big thing about a coil. So even though the PLC outputs 24 volts, I could use it to pick up a relay that's got a 24 volt coil, right? You understand that? And then the contacts could switch what? Could switch AC. It could switch 120 volts AC, or even higher than that. So normally, a lot of your high-powered loads are not going to be ran, or your high-powered loads are not going to be connected directly to an output of a PLC. What we'll do is the PLC will pick up an external relay, and the external relay will run the load. So, and this gave us a few little problems in PLC 1, where some of the students, when they used this symbol right here, they thought it had to be assigned to an input. So what we would do is we'd have a relay coil, and the relay coil controls what? What does the relay coil control? It controls contact. That's what a relay does. So a relay controls contact. Well, what we do is we give the contacts that the relay controls, we give it the same name. And that's also true in PLC. So in PLC 1, we call them symbols. And what's nice about a symbol is once you assign an address a symbol, then you can use what? Then you can use the symbol instead of the address. In PLC 2, these guys call them tags. So the new name for these symbols that we used in PLC 1, we call them symbols. On the new PLCs, they refer to them as tags. So they're basically the same. We have two types of it here. So this is relay logic. So loads on the left, control devices on the left, loads on the right. And what we do is we don't deal in relay logic, we don't deal with rung numbers, we deal with line numbers. So a line is a horizontal line that lines up with another line. So notice these guys, you can't see them on here. So 0, I'm sorry. back up to 2, 3, 4. I can't make it any bigger, guys. Huh? Yeah. And then you can't see it on this side. Let's see if this is the actual U.S. Steel fence. This is a little better. It's a little bit easier to see. So we taught a class for U.S. Steel, and they came out here for a month. So they used to teach, they called it up on the hill. It was a Flint Ridge building up there. They used to have their training up there. And they would send people through that training for a year. And they sent like 18 people through there. And when they gave it and they got out, but it was all self-study. So they sit in front of a computer. And when they got out, they only had one person pass the test. So they sent them out here. They sent us about 18 people. And, they sent them out here for a month. And they went through several things. We were teaching them 8 hours a day. And then, after a month, we had all but one pass the test. So, U.S. Steel, by the way, I don't know, by the way, U.S. Steel is, looking at setting up an internship program here at the college. Similar to the one that we have for both. So what we do with the relay logic is we have a line number. So the way this worked out, this was a page number. So this diagram right here was, at least 137 pages long. And then over here would be the line number. So this would be line number 3. And then, of course, anything that lines up with that would get the same number, right? So they tried to line up as many as they could. So all this would belong to line number 3. So this right here would be a run. So all that's a run. So that's one circuit that runs between L1 and L2. But what we would do is we would come out here on the right hand side and we'd put the location of the contact. So every relay has a name. Can y'all see the names? I covered that one up. So every relay has a name. And then what they do is they come over here and they put the line number that the contact's controlled by that relay where they're at. Can y'all see any that's in my listing? See, 71, 15. Is 15 on it? No, done. And then what you would do is you'd go to this line. So here's line 7, excuse me. The name of this relay right here is 5B3. 5-3B something. H, I think. And then what we would do, we would go down into line 7 and we would look for a contact being controlled by that relay, right? So here's line 7 and here's the relay right here. 3B, 3B3, yeah, this is H. So what we would do is we'd be able to identify and notice, can you see this? The contact has the same name as the relay. So we've been using names for devices for a long, long time, and it makes it real easy to do that. So on RS Logic 500, we use something called symbols. And hopefully, when I took PLCs from me, I required you to use those symbols. And then once you assign a symbol to a relay, then you can do what? Then you can use the name instead of remembering the actual address. 12 rules for standard relay logic. Control devices such as switches, push buttons, relay contacts, and sensor contacts must be placed between L1 and the rump load. Output devices such as relay coils, lighting, small motors, and solenoids must be placed between the control devices and L2. One and only one output can be placed at each line. A rung is an electrical circuit that runs between L1 and L2 that consists of one or more lines. Magnetic motor starters, overload contacts are the only thing allowed between motor starter and coil 2. When you take motor controls, this right here will make a little more sense. All other run loads must be connected directly to L2. Motor starters will have overload contacts between the starter and L2. Control devices can be connected in series parallel and series parallel. However, multiple output devices can be connected in parallel in a different line within a run. Only one output device can be connected in a run line. The rule is one or more outputs on a run, but only one output per line. There are no multi-load series or parallel circuits allowed in the relay logic diagram. Everybody understand that one? Anybody got any questions on that one? Control devices such as switches, relays, sensors with a single contact can only be used once in a relay logic diagram. Control devices that have multiple contacts can be represented multiple times in a relay logic diagram. In other words, the same control contact cannot be used. So when I come back here and look at this little animation, this guy only has, so it's got a single pole, double throw, single pole, double throw. Everybody understand that? Yes, no? Yes, no? Everybody okay on single pole, double throw? Well, what we have is a pole is the number of contacts or the number of switches being controlled by one operator. And then the number of throws is how many positions we can put it in to control a circuit. So this would be like a light switch you have on your wall. This would be what we call a single throw, single pole. Sorry, single pole, single throw. I got it backwards. If I come over and do this, then this would be a single pole, double throw. If I come over and do this, and then I put the dashed line, that means they're controlled as one unit. Right? This would be a double pole, single throw. If I came over and did this, and then I put the dashed line, this would be a double pole, double throw. So this is what you use on a three-way. Electricians call this a three-way switch, by the way. This gives you the ability to control a light from two different locations. So you can turn them on, turn them on. But we could have this, so I could come up here, let me go back. So if I had this, then I could put one contact in one line, and then I could put another contact in another, because it has two switches in it, right? You understand? But I couldn't, on motor controls, I could not use this same switch here twice. So if I call this Rich, and then I come over here and put it right here in this line, and I said, well, this is Rich, and then I come down here later on, and I did that, and I said Rich again, and I screwed up because it's one switch, and I can't have one switch and two different lines, right? You understand? So that would be having the same switch in the bedroom and in the kitchen. It's got to be a what? It's got to be a different switch. So that's what they're saying. If the device has multiple contacts, so control relays, they can have a lot of contacts. So this right here has two. So this right here is a double pole, double throw relay, and relays are often designated by the number of poles they have, and then how many positions that can be put into. So the pole is rated at 24 volts, don't use this current, DC. And the contacts are rated at 10 amps. can measure the resistance of the coil and divide that into 12, and that would give you the amount of current required by the coil. So we could run that off this PLC. This PLC puts out 24 volts. So I could hook that up, and then I would bet that the motors that like run your washer probably don't pull 10 amps. So I could probably run your washing machine with that thing. Couldn't run your air conditioning system. An output device can only be represented once in a diagram. All control devices and output device symbols must be placed horizontally. Signals in a relay logic diagram must flow from L1 to L2. You're never supposed to flow back to L1. A diagram should be numbered and commented correctly. You hate these things where somebody's came in here and did some stuff and they draw this and they give you this thing and they don't document what you do. So if you ever looked at some really, really good PLC programs, they document everything. They document what the rung is supposed to do. They document what the contacts are supposed to do. And then that way, they can send those to us. And then when we take PLC 3, we can figure out how to transpose those programs that were written for Allen Bradley PLCs. We can figure out how to do it on the Siemens PLCs because they commented the rung so much. And we'll show that. A lot of comments. RS Logic 500 calls them descriptions, and 5000 calls them descriptions. And I'll show you how you can actually put a description about the whole rung or about the whole program. So you could actually put that information up in the the first rung of a program. Says this program does this, and it really would help you when you come back 2 years later, you're trying to figure out why in the heck you did something that you did. And believe me, I've been there. And it makes it really, really hard to figure it out. The location of every relay contact controlled by a coil is identified by writing the line number or the contact location on the right-hand side of L2. And adjacent to the coil symbol that controls the contact, multiple contact line numbers are separated by commas. A normally closed contact location is underlined. These numbers are referred to as numerical cross references. This is one thing that we don't have with PLC. So it's very, very important that you give these things names and document or put a comment out there that says where these contacts are at. So we looked at this. Very good print. Like I said, this was provided by U.S. Steel. This is one on number 4 galvanized line. These are revised views for PLC ladder logic. And some of the rules on RS Logic 5000 don't apply, but if you use them, so even though RS Logic 5000 lets you get by with a bunch of stuff, the next PLC you go to might not let you get by with it. So if you follow these basic rules, you can probably program any PLC. You won't have to worry about, well, can I do this in RS Logic 5000 and not do it over here? If you follow these basic rules, then you'll be able to program any PLC. So all of them's in blue. Rule 1, input instructions must be placed between L1, the left vertical rail, and the rung below, the right vertical rail. It should be noted that any instruction that the programming application places on the L1 side of the ladder diagram is considered an input instruction. RS Logic 5000 will do that for you. Output instructions are placed between the rung control devices and L2. Nothing is allowed between the rung output instruction and L2, the right vertical rail. Everybody okay there? RS Logic 5000 will let you get by with a bunch of stuff. I'll show y'all some of the stuff. All input instructions must be placed horizontally. You don't have to worry about that. That's automatic. I don't even know why the rule's in here. A rung output instructions must not be placed in series with other output instructions. Multiple rung output instructions can only be placed in parallel in another line. One output instruction per line, one or more output instructions per rung. RS Logic 5000 lets you get by with this, but another programming language wouldn't. So what I'm saying, if you follow this rule, you could program Siemens PLCs, you could program Allen Bradley PLCs, you could program GE series PLCs, and you won't have to worry about it. You know, RS Logic 5000 lets you get by with a bunch of stuff. Program flow execution must be from L1 to L2. This will give you an error. Rung numbers are automatically placed to the left of L1 of each rung line. We don't have to worry about that. That's done automatically for us. Each input instruction device its address is entered above each instruction symbol. The location is predefined by the ladder logic programming application. All you have to do is just give it the address. All block instructions require a base tag. The base tag is entered in a predefined location inside the device symbol. So we'll have to look at tags and understand tags. So tags are very similar to names. To the symbols that you used in RS Logic 500. But there's some instructions that we don't use addresses, physical addresses. We give them a tag. Each input and output instruction should be assigned an alias tag, symbol name. In new PLC programming applications, these are called tags and are usually required. Once an alias tag name has been assigned, the alias tag name can be used to repeat the assigned logical address within the program by name instead of address. So when we deal with inputs and outputs, you don't have to give them a name. Your counters and your timers and stuff like that, they have to have a name. They have to have what they call a tag. And we'll look at the difference between an alias tag and a base tag. So your block instructions are going to use what we call a base tag. Then your I/O instructions are going to be used what we call an alias tag. So you're given a name to an address. Does that make sense? Or to a physical address. Rule 8, optional comments descriptions should be added to each instruction symbol and rung. Rule 9, the instruction tag should be given a name that relates to the instruction's function in the control circuit. Use of tags allows logical addresses to be addressed by name instead of number. Input and program relay contact instruction addresses can be used multiple times within the PLC. So this is what's neat about a PLC. So if I've got a switch in a relay logic and it's got one contact, I can only use that contact how many times? One time. I can assign a single pole, single throw input switch over here on this guy, and then I can use the contacts controlled by that switch as many times as I want to use it. So that's a big difference, and that's made a big difference, especially in sensors. So input program contact addresses can be used multiple times within a PLC program. Output enable instructions address should only be one. So output enable instructions should be only used once. The output latch and unlatch. Hopefully y'all got through those in PLC 1. Some of y'all didn't, but I know we lectured in my class. So technically, this I don't want that. So RS Logic 5000, there are two logical addresses. So we don't understand physical addresses. So I pulled this off. There's a thing you can search for. It's called System Information. And this will show you the binary addresses assigned to every device inside your computer. So do you have to know the time is at 40 hexadecimal? Do you have to know all this stuff? Do you need to know these physical addresses? No, because you're giving them names, right, or reference them other ways to applications. So what we have to understand inside the computer, every address, every physical address is a binary address. So when I first started programming microprocessors, we had to learn all this stuff. We taught a course where we actually built expansion cards for the computer, and we have to assign them an address. This was a binary address. Of course, when you display this in your computer, it don't do it in binary. It does it in hexadecimal. So normally we don't have to know the physical address of these devices. They want to make it a lot easier for us to understand. So what they do is they assign it a logical name. So when you came up here in PLC 1 and you said input : 0/5, would that be a physical address or would that be a logical address? Well, no, the physical address might have been something like this. But what our computer does, it allows us to use these logical address, and then the application translates it over to the physical address port. So when you compile that program, what it does, it sees that input 0.0, it knows where that's at inside the PLC, and it actually uses the physical address inside it. So what we deal with is logical address. When we program a PLC, thank goodness we deal with logical address. Because that means if I wanted to send something to this display, I would have to know, for me to do it, if I was writing a machine language program, I would have to know the address of the display. And I would have to know what codes to send that display controller to tell it to do certain things. But thank goodness I don't have to do that, and that's why we have drivers. Y'all heard what's a driver? Software driver. What's a software driver? Huh? Driver? Yeah. It controls hardware. So the operating system is just a bunch of drivers. That's all it is. Thousands of drivers. So when you say store something to your hard drive, you don't have to know the address of your hard drive. All you got to do is tell your operating system you want to do it. So every once in a while, when you plug a USB thing in here, what is it? A little box pops up saying, "I'm installing software." Well, what's it doing? It's installing the driver that allows your operating system to access that new device. Thank goodness we can do that. So instead of me knowing that the speaker is an address, it's a 16-bit address, by the way. So instead of me knowing the speaker is at 00000000001100001, I don't have to know that. I just say play music and it comes out my speaker, right? You understand? Because the operating system knows what this is. So what it does, it allows us as users to not deal with the computer on the binary level. It allows us to deal with the computer on so these addresses right here are logical addresses. So when I compile this over and it takes that and converts it over to the binary program, it knows the address of input 0/5. It knows the physical address. So this is what they'll call a base tag. Let's take a 2-minute break here. I think we've gone through optional comments should be added, tags should be given, name or languages, contact instructions can be used multiple times. Physical addresses of a device on a computer is always binary, so we just got to talk about this. In RSLogic 500, the address input : 0/5 is technically a logical address because it is not the actual binary address of the program. So these are translated when you compile the program over, right? The logical address is translated by the PLC programming application to the I/O port physical address when you compile it over. So what's compiling? It's when you take a program written in a high-level language and convert it over to its equivalent machine language. And so that's what you do when you download it, you're running it through a compiler, right? You understand that? And then when you upload it, you're uncompiling it. So that's a pretty neat application. Once they came up with compilers, it made writing programs a heck of a lot easier. So in RSLogic 5000, also Studio 5000, there are two logical addresses associated with an instruction. A base tag has a memory or I/O allocated for a storage or retrieval of data. An alias tag does not contain any data. It simply redirects the access to a tag that does contain data. So, alias tags is what we will assign our I/O device. So input 0, input 1, input 2, we'll give it an alias tag. So basically an alias tag is tying a name to a input-output device. So this is what we did for symbols. A base tag is a tag that we assign to a block instruction. So like a counter. So what we're going to find out in RSLogic 500, those data files are gone. So all those T4s and T5s and all those are gone. We control the memory. So what we do is we'll give a counter a name, or we'll give it a tag, and that's going to be a base tag. Because it's not going to be tied to an I/O port, right? You understand? It's going to be tied to a memory location somewhere. So if I set up a timer, we're going to have to give it a tag. And that tag is going to be a base tag. If I set up an input port, and I want to give it a name, then that name is called an alias tag. So alias tags are the same that we use symbols for in RSLogic 500. Okay? And when you assign the timer a name, that would be what we call a base tag. So this is the address, this is the logical address for input. It's a lot different than RSLogic 500. So that N:0/0 is gone. So first of all, you have to identify if it's attached to, if this is internal or to a port attached directly to the PLC. If it addresses an input port on another rack or another PLC, then it would not be local. So all our logical addresses for input. So this would be local : 1. So that means, so the internal module, the internal ports are no longer 0, they're 1. Then we come up and we would put a colon, and then we'd put an I or we'd put an O, depending on whether it's what, input or output. And then we put then we type in data, then we'd put a dot, and then we'd come in and we would say what bit on that input port we were interested in. So slot 1 number in which the I/O module resides, 1 for internal I/O, I for input, O for output, data, dot, 5 would indicate it's bit 5 within the current word. That makes sense? This is a base tag. So this is actually pointing to a device that's inside the PLC memory. Everybody okay? Now, when I come up here, this, by the way, this is right out of the Siemens training. A base tag is a digital representation of a physical address of an I/O port. So this would be a base tag. An alias tag or reference that once assigned can be used instead of the base tag logical address. So this would be the alias. So for this input, data, a local, which means it's what? Is either internal or attached directly to the PLC through where we can add modules to this thing. One would be what? Internal, right? Then we put a colon, and then we said what? Sorry. I would be what? So this would be one. I would be input, data dot 3, and then we put the number that we want. But once we assign this the alias push button underscore push underscore button underscore 4, then I'm through with that logical address. From then on, I can use what? I can use the alias.
You have an address symbol like the last one.
What do you mean?
So, for example, we know all the buttons, all the inputs, we go to an address symbol. So, if you remember, like last time, you can go and put in everything before you start to write the program.
Yes.
You still have that same opportunity.
But you'll have to identify what type. You'll have to identify it as either a base tag or you have to identify it as an alias. And we'll show you how to do that. So there's a tag symbol, just like on the RSLogic 500, but it's right by the program. You don't have to go all the way down. The local tags are directly under the actual program itself. And it's actually a little easier if you do it on the fly, because what it'll do, it'll assign it to the right numbering system, or I'm sorry, resolution of the number of bits that we're going to use. And that's another term that we're going to have to learn how to use. So the base tag would be something that, understand, a base tag would be like a counter. So a counter would get a base tag, because it's just a counter. It's gonna be memory, but it's not going to address a what? It's not going to address a logical input. An alias is what we're going to assign. So all our inputs and all our outputs need an alias tag. So base tags are usually required. Alias tags are usually optional, but we're going to use them anyway. Because once you assign it that alias, then you don't have to remember this big old long syntax for these inputs and output ports, right? And by the way, if you do it right, you don't even need to do that, and I'll show you something that's really, really cool. So we'll bring it up. I'm going to bring up, so on your, if you got one of my computers, if you're using 1 through 11, don't use 6 for some reason. It won't connect to the internet. I can't get the wireless to turn on. It says that when I turn it on, it says it's been disabled. So what you have is you have this little circle down on your taskbar. Now I've got mine really, really small. This is RSLogic 500 or 5000. And the big difference between RSLogic 500 and RSLogic 5000 is the first thing you're going to do is you're going to assign the name. So on RSLogic 500, it didn't ask for a name until you saved it or until you downloaded it to the PLC. So we'll start a new project. So this is different. By the way, your current use projects are going to be down here. Of course, you're going to point yours toward your USB thumb drive, right? And what's the first thing it's going to ask me? Well, it's going to ask me to select a what? It's going to ask me to select the CPU. Now, luckily, expansion modules go on the right, so they put all this information on the left. So all this is available on the left. So when I come over here and look at this, it's a 53070 controller, Compact Logix 53070. And then these are all the models that we have available. And when you look on the side, it says ours is a 1769 L24ER PC 18. So what I'll do is I'll just come up here and select that. So that's kind of similar, right? And now it's going to ask, huh?
Is that how we go on up under?
Ours is 1769
No, you don't have this PLC.
Oh.
You got that's the micro logic. Y'all gonna unmount the PLCs that we used in intro. Some of y'all was over on the other class. You're gonna unmount these, you're gonna use the cable, and you're gonna mount your own PLC. They're back there on the table. So no, it's nowhere near the same PLC. So this is this one. You can tell there's a lot of difference. So that's a really good point. So that's the MicroLogic 1100 right there. That is programmed with that's an RS Logic 500 PLC. So that's the one we use. This is our compact logic right here. And of course, what's nice about the EduTrainer is that we can mount any PLC we want to. It's really, really neat. So it mounts on a DIN rail. And so it snaps in the bottom. So the first thing you'll have to do is when you unmount that one is get a little screwdriver and put it in here and pop these two tabs down on your PLC. And then we'll have to come in and unscrew these modules and take away the connectors that actually connects it down here. And then we'll figure out how to insert these things up in here to program. So that's a really good question. So no, you don't have this. Then we'll give it a name. So that's a big difference. By the way, if you put a spaces are not allowed in this. So what you notice what it automatically did when I hit the space, it put the underline in there for me. And that's also true on tags. And then I say next. The next it is asking us, do we want to assign this a password? Of course, what you're going to say, you're going to say no. So you're going to hit finish. And then it's going to load it up. So far it's pretty similar, right? It's a little different. So on the 500, as soon as we set up a new project, it came up and asked us for a what? It asked us for a PLC, but it didn't ask us for a name. This asks us for a name. And I don't know if I'm communicating with my PLC. If it's not, we could. And you're going to see a big difference in the project tree if it ever comes up. It's still in the same. The project tree is still on the left-hand side. And it's going to look very familiar. Of course, I got a little problem with mine. I got to come back. So they call it Studio 5000 Logic Designer. And then it comes up to the blank screen. Since this is a new program, if this is one that you were loading, it would load up your other. So I got a little problem with mine. I've screwed something up. It'll still be okay for this. So the first thing we're about to learn, and I need to bring that slide up, is we got three ways we can represent numbers. We can have binary, ones and zeros. There's it's an industry International Electrotechnical Commission has came up with a way that we document the size of a number. So back in PLC 1, we learned we had bits, we had bytes, we had words, we had double words, and then we had quad words. Well, PLCs don't quite get that nomenclature. Bits, if you're using a single bit, they call it boo for boolean. So boo. Then when I deal with a byte, we'll call that a byte, a word, a long word, and then a double long word. But it's not quite like that. But we'll look. So here's my project tree. Y'all see it over here on my same side as it was before, right? Notice there's no data files. There's no 0, 1, 2, 3, 4, 5, 6. There's none of that anymore. Because what you're doing is you're controlling the memory. So I'm going to come up here, and here's your main program, your main task. It means it's a constant running program. I'm going to click on the down arrow. It's main task. So the actual program, I'm going to click on main program and the main routine. Now see how I got to the main routine? Yes? Okay. And then I'm going to come up here and double click on that, and it comes up here very similar, right? Except for the end being down here and here. So here's our first rung. It came up there sitting on our first rung. Okay. So, and this is laid out almost exactly the same. Your palette for your instructions. Favorites, they call it favorites instead of users. Then alarm, which we're not going to use bit. Timers, counters we're going to use. Compare instructions, math instructions, move instructions. If I want to move through them, I'll come up here and just click on that. And in this class, I'll show you how to add stuff up here to these favorites if you want them up there. So here's my down drop. It does it exactly the same way as Arch Logic. Let's say we'll come up here, we'll pull down a very simple contact, and then I'll pull out an output enable instruction. Now, we got two ways we can deal with tags. We can have what we call controller tags. Controller tags, in this class, we're going to start dealing with subroutines. The subroutines is when you take a very large program and you break it down to smaller ones to make it more manageable, make it easier to troubleshoot, makes it easier to come back and check things. Well, a controller tag is shared across everybody. A local tag would be shared by just this section of the program. It wouldn't be shared through multiple subroutines. Okay, does that make sense? So here's my tag table. So here's the tags. These are the tags that's been assigned. If I want to enter my tags in front, I would come over here, and I would come up here, and I would start typing. Okay, so I could call this, I'm going to call this input 1. Now this is a tag. Now is it a base tag or is it an alias tag? Well, notice when I put a space, so your tags can't have spaces in there, it'll automatically put an underline. Okay, so right now it's set up for a double signed integer. We call it a dent, so we're going to have to learn that. So by default, it set it up for a 32-bit signed number. So if I'm going to use one of my inputs, then one of the first things I'm going to have to do is I'm going to come up here and have to assign this to a single bit. They call it bool. So that's a single binary bit. Okay. Then it's an alias for. So I'm going to say, okay, an alias for. So this is the alias. Then I can come over and click this. And this brings up my input-output devices because I've called in an alias, right? You understand that? So I'm going to deal with local input. We're not dealing with C. We're not going to talk about that right now. But that's the second one down where it says local 1 : N, right? You'll see that. I'm going to come up here and just click on the little arrow. Then I'm going to come down here to integer. I'm going to click on that. And now it's pointing to the inputs that's available. So I'm going to come up here and I'm going to choose input 0. You can put descriptions out there. Okay. So now when I come over here, so I'm calling this input 1. If I go back to my if I come back to my main routine, and up here I type in input 1. It should be in there. Well, I don't know why I didn't put that. Oh, wait a second. Let me see if I saved that yet. Local tag, edit tag, input 1. Local tag.
I'll just go that's a lot. Stop it in.
It should be. It shouldn't require that, but we'll try that. It pulled up, so I pulled it up, and I can hit enter, and it automatically assigned the base tag to it. See that? You'll see that? Another thing I can do, if I wanted to do it on the fly, so that's the way I could go in and I could go ahead and assign all my tags. Or if I wanted to rename it, I could go up here to what? Local tags. I could go to edit and I could give it another name. So if you needed to rename the tag, if you needed to assign it to another input. But what we had to do is we had to define it as a double integer or a single bit instruction. Y'all understand that? As soon as I said it was a single bit, which is they call bool, by the way, for Boolean, then it automatically allowed me to set up the alias for that. Okay. Another way I can do it, I'm gonna go back to my main routine. So let's pull another contact down. Is I can come up here if I want to do it on the fly. I can come up here and right click on it, and it says I'm gonna do a what? A new tag. Okay, and it brings this up. But off the bat, it's going to assign it to a base tag. It's going to be an input port, so I'm going to give it an alias. So I'm going to come down here and say it's going to be an alias. And then as soon as I said it was going to be an alias, then it came up here and automatically changed this over to the Boolean, right? But you can change it if you want to, but what it's trying to do is figure out what's the most logical category of numbers we're going to assign this to. And up here I can put input 2. Okay. And then now alias 4. So this is the alias, this is the name for an input. So now I can come up here, the same thing popped up. This is an input. I can click on the little arrow, then I'll go down here to integers, which is this guy. And now notice 0 is grayed out because I've already what? Assigned it. So now I'm going to assign this to 1. I don't have to assign it to 1. I could assign it to, on mine I could assign it to 15. And then when I get through, I just say what? Create. So this is where you would do them what? On the fly. Or you could do them up front. But you have to know what type of number you're dealing with. So over here, this is my output. I can come up here and right click on this. Say what? New tag. All right. We'll call this output. And then space 1. I'll put, spell it right. Okay. And this is an alias tag. So I'm giving an input port a name, right? Understand? So alias. It automatically switched to bool, right? And then I can come over here. Now I'm going to come down here where it says what? Local 10. You'll see that? I'm going to click on that. Then it's going to be an integer, by the way. And then I'm going to select output 0. Then I'm going to say create. So what it'll do is these addresses, these base addresses for your input and your output, the syntax is hard, but we don't have to do it that right because we can just go in there and select an output. We could type it in, or we could select an output instead of us trying to remember the syntax. But if I was to come up here and use a bigger instruction like a counter, by the way, I just found this out today. If you highlight the rung, and you know the instruction you're going to put, you can just come up here and type CTU, and you can hit enter, and you don't even have to go through the template. And that so I just did what? Highlight the rung, but you got to know the little 3-digit acronym. So here, this is a counter. Well, there's no T5s. There's no T5s. There's none of that stuff. So what we're going to do is we're going to assign this a base tag because it's not going to deal with a output or an input. So this is just going to be a name that we're going to assign some memory. So what would I do? As soon as this thing, I right click as soon as the thing starts spinning. I'll right click and say what? New tag. And it automatically chose what data type? Counter. So if I was doing it under the edit tag, I would have to choose that data type. And then we'd give it a name. Counter 1, counter 1 or whatever we're going to call it. And now I'm through, because this is, by default, it comes up as a base tag. So alias is when we're dealing with one of our input ports or one of our output ports. And what we're doing is we're giving those logical addresses a name. Counters, timers, anything else is probably going to be base tags, right? You understand? Because this is not dealing with it. This is a counter. It's not alias for anything. It's a what? It's a count. And then I'm going to create. And so now that counter has that name. By the way, presets are exactly the same as they were for RS Logic 500. We can enter a value in here. I wanted to preset, like 100. And then notice it's still got the what over here. It's got the done bit over there, which tells us when it matches that count. And what happens when it hits that count? It keeps what? Keeps counting. So here I don't have to worry about T1s. I don't have to worry about T4s. I don't have to worry about T5s. We're managing the memory. So this is what I was saying. On RS Logic 500, every counter took 3 words of memory. And it automatically assigned 256 counters. It assigned space for 256 counters. Whether I did what? Whether I used them or not. So that was over 1K of memory just for what? Just for counters that I might only have one or I might not have none of. Right? You understand? Here, this thing only assigns the memory when you create a counter. So how much memory are we using? Well, I don't know. These are using double integers, which is 32-bit numbers. So this guy right here has got to use at least, 4 or 5 words of memory. So that's tags, guys. So y'all understand the difference between an alias tag. So when are we going to use alias tags? For inputs and outputs, right? When are we going to use base tags? For everything else. For everything else. So counters, timers, everything else, you're going to give a name. And if I wanted to address the done bit, well, let me go back to my favorites. And let me put another run here. Go back to my favorites. If I wanted this to come in when my counter was done, now I come up here and I say counter, and then I say dot, so there's no slashes, and then I choose done. So everything inside here, so now I've assigned this contact to that coil reference. But we still have to specify done, we still have to specify, ACC for the accumulator. So the abbreviations are exactly the same as they were under 500. But once I've assigned it what? A name, then we can use names instead of course, here we don't call them names, we call them tags. But a base tag, every one of your logical instructions are probably going, every one of your block instructions are probably going to use a base tag. Your inputs and your outputs are going to use an alias tag. That makes sense. Everybody okay? So inputs, we had 16 on the RS Logic 500. It automatically signed 256 words through inputs. How much memory we're using now? We're just using memory for what? For three input instructions, with three of these. So questions. So you can see it's very, very similar, right? What we learned back in RS Logic 500. Very similar, except we're going to get into more of these advanced instructions. We're going to get into timers and counters are what we're going to pick up. But look, they're the same. T on, that's an on delay timer. T off, that's a non-retentive off delay timer. RTO, that's a repetitive on delay timer. CTU, that's a count up. CTU is a count down. And RES is reset. That's exactly the same instructions we had with in RS Logic 500. We're going to look at compare instructions. You can read about them in your book. They're going to be exactly the same, as far as what they do. But they're not going to be. They're not going to. We're not going to assign a data file to them. We're going to assign a tag to them, right? You understand? We're going to look at math. So compute, which is CPT, is a really, really interesting instruction. The book doesn't cover that, but we will. We can do what? We can do add, subtract, multiply, divide, mod, I'd have to look that up, square roots. I can't see what those ones are. Absolute value and negate. We'll have to learn a little bit about negate. I don't know, I've got a mark on my board up there. But most of y'all understand those. Move, we're going to pick up some move instructions. More move instructions. Move with math, and our logic. This is not contact logic. This is what we call bitwise logic. So bitwise means we're going to take one whole word and we're going to add it with another word, or we might add it with a byte, or we might add it to a double word, right? You understand that? So these are going to be sure enough and. So it's not contact, it's bitwise. So we can add a bunch of bits, we can OR a bunch of bits, we can exclusive OR a bunch of bits. We got a NOT instruction, we got a SWPD, I'd have to look back clear, and PDD, I'd have to go back and refresh myself on those guys. So we're going to look at those. And we're going to look at shifting. How do we shift instructions? We're going to figure this out. Sequence. So here's your shifts. Bit shift left, bit shift right. These are stack instructions. We'll have to learn about stack unload, stack load. And sequencers. I think it's about the last. And program control. Jump, label, jump subroutine, return, SD, subroutine, and we'll look at some of these when we actually get into this course. Unfortunately, we don't have time to go through all these instructions, but we do give you the manual. So one of the main manuals you're going to look at for reference is on Blackboard. It's inside inside course content, right here. Inside reference material. And this is where the assignments will be at too, guys. And then this general RS Logic 5000 general instruction reference manual. This will probably be the main one that you're going to use. It actually explains the different instructions. Sometimes it gives you the syntax, sometimes it don't. I try to give it to you in the PowerPoint. So questions? So, yeah, okay, so it's a little different, but knowing RS Logic 500 should make it probably real easy to adapt 5000. There are some differences. It's tag based, and in RS Logic 500, symbols were optional. Here, the only time symbols are optional is it for your input-output ports, but you don't need to do that, right? You need to make sure if you typed in that address, if you learned that syntax and typed it in, you would not have to assign it a tag. So you can get by with that, but you can't get by with it on your block symbols, your timers, your counters. You don't have to use base tags on those things. You've got to, because you don't specify a T file anymore. Okay, guys, we're going to take a break. 10 minutes. Let me go get the stuff to figure out how to wire these PLCs. It's very, very similar to anything that I use. All your programs will be saved on your student-provided USB thumb drive. USB drive will remain in the instructor possession during your entire course. It will return to you at the end of the term. So that way, all I got to do is just delete the programs off the thumb drive, right? At the end of the term. And I showed you how to point it to your thumb drive, right? We need to make sure we know how to do that. Sometimes we're going to be in teams, sometimes we're not. This is going to be something new that we're going to try this semester. But like I said, to write your program, you do not have to be connected to a PLC. You didn't even have to do that in RS Logic 500. When did you need to be connected to a PLC? When you're ready to download your program, right? That's when. That's the only time. So even though we're only going to have 6 of these, we shouldn't have any problems. So some of y'all are going to have to get together a little bit when we start wiring these things up. So I think we got how many out there? We got 7. How many of these EduTrainers we got? So we got plenty. We're only going to need how many? 6. Because that's all the MicroLogic, that's all the Compact Logic PLCs that we have. So it's going to be about the only time we'll really do a team lab is when we wire them up. After that, we'll just rotate between PLCs. Need to place check marks beside your steps when you complete them in your lab book. When you name your program, you need to name them according to this syntax. Y'all see that in this paragraph right here. So lab 5-1, so that would be group lab 5-1, and then you put your initials out there. So that's the way you'll name your program. So the one that's in the lab is if you was working with a team, then that's the way you'd name your program. Okay, that makes sense, yes? That's just something I made up. So this is Bill Irwin Fold and Grace for me. So these are team members. So Bill Irwin Fold, Bill Fold, that would be his 3 initials, and Grace for me would be these initials right here. So when you write your program, you're going to just use the lab section, right? Like 5-1, lab 5-1, and then your 3 initials. When you need a lab sign-off, odds are what you'll probably do, we'll see if it works. If it don't, we'll figure out another method because of the way we set up communication with the PLCs. I think I can switch over and do it that way. But we could actually just, when you're ready for a sign-off, I don't even need to do what? I don't need to come back there. You can do what now? You can bring your thumb drive to me, and I can download it into my PLC and see if it works. Which is what they do, by the way, if you take the simulation class. That's what we do. So I'll probably be able to sit here the whole time. I wish I'd have thought about this last class. This would have been really neat. Because, I don't get around when I walk. I don't walk, I waddle. And I got to touch something when I walk. So, but you're going to demonstrate your program, right? You understand that? Just like we did in PLC 1. You'll tell me what it does. I'll flip the switches. You'll say, well, it's supposed to do this and this and this. But like I said, these programs here, you're going to have to try to figure out how to do it. Demonstrate your working problem. If you're not stapling multiple lab groups together, right? You'll put them into this box. The name's going to change on the front of this box. Advanced PLC Labs to be graded. There'll be a folder over there that says not ready to be graded, that you need to make sure you get it in the right box. If you put it in the to be graded and it's not ready to be graded, it's going to be what? It's going to be graded. So if you don't do one of the activities and you turn it in, then it's going to be graded. Oh, by the way, anybody that want, well, I can't find y'all that took the PLC 1 last class. The time before that, but I don't have y'all's labs anymore, but the one that took it this first semester, if you want your labs back, I can give them back to you. So I'm going to keep them the whole time. These are the list of the labs. So the first lab, hand out lab 1, activity 1 is going to be wiring the Compact Logic 370 PLC. And then we'll get a little more in-depth introduction into Studio 5000. We'll let you do a little programming instead of sitting back there and looking at it. And of course, this gives you some detailed information about math instructions. We need to make sure we understand what dents are, what ints are, what fents are and bools and stuff like that, because if you ever watch any video, that's the way they explain them. They say, oh, that's a dent. So we'll explain those different categories of numbers systems we'll look at. So this gives a really good explanation of what I require in those labs. So these are the labs we're going to try to do. We're going to do math instructions, counter and timer. We'll just use the ones in the book. Then we'll do math instructions, compare instructions. Then we'll do jump, master control. I'm going to add, there's not a logic in here. I'm going to add another lab in here that covers logic. We'll look at jump and master control. Two sections of this, guys. Subroutines. Bit shift left, shift right, stand up, sit down. Okay. Data handling instructions, sequencers, and I'll add a small lab in there on bitwise logic and explain that to you. So we know we can do logic on using contacts, right? But what we'll find out is we can do logic on a whole word. I mean, a whole word or a whole double word. We can do logic, and they call those bitwise instructions. We'll make sure that we cover that. I know it's covered in the lecture. And of course, this is the way you'll be graded, how I mark off points. So it's basically the same as we did before. So our first lab we're going to do is we're going to, this thing's stapled on the bottom side, guys. You're going to be my go-to this semester, right, Jenny? That's one thing for sitting on the front, but at least I do shower, though, right? So this is going to be our first lab. First of all, what we're going to do is we're going to take the Compact Logic the MicroLogic 1100s. We're going to take those off the mount, and we can go ahead and take it off all of them because we'll use them. If you take PLC3, and what's neat about the EduTrainers, for one thing, the trainers for the Allen Bradley Festo trainers for Allen Bradley certification were almost $9,000 a piece. No. So when we were there, Nancy's got a lot of pull with Festo. We got these approved right here. These are about $2,000 a piece. So we saved $7,000. So these are approved for level 1. These are EduTrainers, and what's so slick about you buy their trainers, you're stuck with one PLC. You buy these things, you can mount almost any PLC that you want to. Because the primary way of mounting, I don't have one of the Slick 500s over here. I wish I would bring one over here. Because it's got a rack-mounted chassis. It's a chassis that you plug into a rack and it hits a slot on the back. These the way we do, and we have a backplane. The backplane actually runs through the PLC. So now what we do on these PLCs, whether they're modular PLCs or they're hybrid PLCs or fixed PLCs, is normally we mount them on one of these, this DIN rail back here. This is called a top hat DIN rail. Can y'all tell why? Because if you turn it upside down and set it down, so this is called a top hat DIN rail, and this is a standard size. So what you'll have to do to take the MicroLogic off is what you're going to do is the first thing we're going to have to do is we're going to have to open, let me bring up my camera. And these input modules and these output modules supports a word, a 16-bit port. But we're only going to use 8 of them. So the inputs we'll use, some of y'all already had that when we when we set up. So what we'll do is, before we start taking it off, is we'll come up here and we'll remove, let me just point the thing down. Make sure we turn it off right and unplug it. Another thing nice about this PLC is that it powers up off the edge frame. So we'll run this up there. What are we doing?
Yeah.
Oh, okay.
Do we need screws?
Yes, you'll need a screw. So what you'll have to do is you'll have to,
Go ahead and tell us now. Push it through back. It's a little battery you got. Full good job. I've been shooting your hospital.
so what we're going to do before we unmount the PLC, by the way, it's easier to wire the PLC before you mount it. So we got 4 screws here, right?
Can you blow it up? Can you make it to?
Yeah, I can. Hold on. Is that good?
Yes, sir.
So we got these 4 screws here. This holds the inputs. Now, so this is the way we're going to wire. So these ribbon cables come down to these 2 modules right here, these 2 connectors right here. You see why they call them, some people call it flat cable, some people call it ribbon cable. If you look at it, you notice one has got a stripe on it. That goes to pin 1. That's 1. And these are 10 wire ribbon cables. One of them is plus 24 volts, which would be the red. And then the minus is over here on pin 10. Y'all are not going to use both of these. You're going to just use one of them. So what I have on there is I've got the wiring, the wiring of these modules. Hold on a second. Yeah, because I've got 16. So these modules support 16 inputs and 16 outputs. On my PLC, I've got 16 inputs and 16 outputs. So that's why I've got both of them. Each one of those connectors can handle 8 inputs or 8 outputs.
But are we moving to that though?
Yes, but you need to know which one you need to remember which one yours is hooked to, because that's the first 8 switches. You understand what I'm saying? Does that make sense? So remember which one it's hooked to. So we got a drawing of it too. Let me bring up the handout that I've got. I'll get you. So you should have one cable going to your input and one cable going to your output. The connector is in it's called SV1. That is for your first 8 inputs, and then SV2 would be for your second 8 inputs. The problem is on the input module, they did not put the numbers up there. So that means the one that is plugged into now is SV1. But when you look at the output module, they did put those names on there.
So we gotta take this.
Yeah, make sure you don't pull it by the cable, pull it by the connector, right? Everybody understand that? I hate people that do that, unplug extension cords by pulling, and then they complain. Or chargers for their cell phone, and they wonder why their cables keep what? Breaking. And what you see what they do? No, that's the power. Yeah, don't mess with this. This is the actual power coming to the module. The only thing you're going to take off is the ribbon cable. So you're not going to touch this down here. This is the power. This is what actually powers up this module. So Brown, are we okay? That makes sense? We okay? I'm going to do the same thing with the output. So it should only have one on there too, right? Now once you get both those off, then what you're going to do is you're going to take your small screwdriver, and what did I tell y'all to do? Pull the little tabs down, and then you should be able to roll the PLC up to the top. Y'all understand that? That makes sense?
No, right back.
Yeah, they're right up here. So mine's black. So these two tabs right here. So you have to stick your screwdriver in there and pop them down. And then when you pop both of them down, you'll be able to pull the PLC up. And once you pull both of them off, then what you're going to do is you're going to do what? You're just going to roll the PLC up and it comes straight off. And feed your cables back up through it. And what you do to put it back on there is you just push the tabs back up. And then you do what? Put it on the top and then push it down and it'll lock back in. So you'll do that to the new PLC. But what we're going to do is we're going to wire the PLC up before we mount it. Everybody okay? So you're going to have to get all that tape off there that we used just to clean it up, which is what y'all do when y'all finally get your PLC routed. Or if you don't, you won't be able to tell the numbers of the wires. Huh? What's that? No, we're not. So take PLC through, what are you going to do? You're going to take these off, put a zero on it. So what we use is injectors, companies, we use those for right.
Take all the tape off?
You got it? Is that okay? What are you laughing at? Oh yeah, I did. Sorry.
Oh.
These connectors are really neat. I don't forget what they call these terminals, right? Yeah, we need to cut that. And we might need to look and see, verify it's got the power wires in there. They should be taped up. But when you pull off, you might have to pull out the power module. If not, we might have to.
Should be two little wires.
Should be a red one and a blue one. Or it should be a colored wire. It should be taped up on the end.
Come on this side.
Yeah, yeah.
The red and blue okay?
Yeah, it's behind the power. So this is the power control right here. And then you can see, so the red is the plus 24, the blue is the minus 24, and you should have two wires coming off those two things. So mine looks like this. So we need to bring those out. If it's got any tape on it, you need to untape those.
Let me find that out. So I was trying to make
These right here.
You gotta pull them out the top.
Now you'll have to pull them eventually, but you can. So that's your two power. That's 24 volts. The MicroLogic 1000 is an AC/DC relay PLC. This is a DC/DC/DC. Y'all remember what that means? DC/DC/DC. You know what that means? Powered by DC, inputs are DC, and outputs are DC. The 1100s, the 1100s are AC/DC relay. So that's why you got a power cord coming into the 1100s. They've got their own power supply now. Yeah, you might have to pull the module out itself. The actual power control module. I'll show you as soon as I find mine. Now they show up. So you should have this drawing right here. And then if you look at the PLC, you'll see a label. Unfortunately, it don't line up as good as this. You might not. Is that socket? There you go. Okay, can y'all see this? You should have this in your handout. By the way, this came out of the installation manual, which is over. It's part of your reference material. So I just cut and pasted this out of there. So this is the layout of the inputs. Got 16 inputs and 16 outputs. So according to this, input 0 to 7 are here, and 8 through 15. Then we're going to run 2 commas, right? Understand that. And then down here for our output, we're going to run our plus, 2 pluses. We got 2 separate wires, right? Understand that. And then we're going to run another comma down here. So we got 2 of these. We got 2 tables. So 2 tables, we got 2 24. So that's the red wire. So 1 second red wire, that's the what? That's plus 24, and that's on this guy right here, by the way. And they run in sequence. So pin 1, that's the one with the red stripe. So the one with the red stripe is pin 1. The one beside it is pin 2. Pin 2 controls, well, pin 2 is going to go to what on that? It's going to go to input 0. Pin 3 is going to go to input 1, input 2, input 3, input 4, input 5, and then what's this say? 6, I'm sorry, then it moves over. 6, now this is input 6, alright. This would be input 7, this would be input, so input 7, that's our 8 input. And then this guy right here is this, I'm right. Look at the right hand on that one.
And when you say bridge track, you're talking about from these little,
I'm looking at this cable, and then this red one that's plus 24, and then it goes right down the line. So the one right beside it is input 0, then what's next? Input 1, input 2, input 3, input 4, input 5, input 6, input 7. And then conductor number 9, the one on the other side, the opposite side of the red is your minus 24. Y'all understand that? Yes or no?
no. One second.
This is plus 24. This is minus 24. Plus 24, minus 24. So if I was to number these 1 through 10, then 1 is plus, 10 is minus. And then they fall right down the line. So what's beside? So here's plus. What's right beside the red? Well, that's input 0. So we're going to connect that to input 0 on the switches. Right beside that would be input 1, input 2, input 3, input 4, input 5, input 6, input 7. Y'all understand that so far? Okay. So all we got to do, when I plug that thing into here, then this is wired for this guy right here. All I got to do is take this other side, the one that's got all the terminals on it, and figure out how to hook those up to the PLC. So and these just push in, by the way. In fact, on this one, you can just push them in. To get these things out, so let me bring my, yeah, okay, sure. I should have told y'all to go ahead and do that. Of course, we've only got 6, right? So some of y'all are gonna have to look on with somebody if you're slow. So that wasn't the right wiring. Let me look at, it's not the right, let me find the book.